Hello friends, MoNaCo here with a video on the pH scale, what it is and how we've arrived at it as a tool. And we want to understand at the end of this video that each step in the pH scale represents a 10 times change in concentration of the H plus and the OH negative ions. That's the main point here. We all know the pH scale exists. It's a direct or indirect measurement, however you look at it, of the concentration of the H plus and OH negative ions that are dissolved and dissociated in a solution that makes it acidic or basic. Okay, so pH scale, power of hydrogen, that's what it represents. pH is power of hydrogen. It represents how acidic or how basic something is. We all know that the scale goes from 0 to 14. Memorizing which side is acid and which side is base is up to you. You got to remember 0 to 7, acidic pH, neutral 7, basic 7 to 14. Okay, the only neutral substance is water at a pH of 7. That's the main point there. Now, the pH is a logarithmic scale, which means that it's based on the number 10, powers of 10. Log of base 10 of 10 is 1. So I got my calculator here. I'm just going to do log of 10 is number 1. Log of 100 is number 2. Log of 1 is number 0. And log of 0.1, or 0.01 is negative 2. This has to do mathematically with raising 10 to a power. 10 to the first is 10. 10 to the second is 100, etc., 10, etc. 10 to the 0 is 1. 10 to the negative 2 is 0.01. That's this relationship that we're talking about. Now, pH is the negative log of the hydrogen ion concentration. That's what this is. Hydrogen ion concentration. Now, you don't actually have to do this on any of our tests or exams, but this is the mathematic way that it would be calculated. If a solution has 1 molar concentration, we put the 1 molar in the log parentheses and put a negative on it. So negative log of 1.0, the pH of the solution would be 0 pH units. That would be highly acidic. So what we're doing here is we're just taking the value of the concentration and putting it in there and calculating the pH units with a calculator. That's really all there is. Okay, so I'm not going to do much more of that because you're not going to have to do it on your tests or quizzes either. Now, the other side of things, for a basic solution to find out the solution's pH, you do the same negative log of the concentration, but you take the answer away from 14. So in this scenario, we take our concentration, put it in there, and we just take that answer, negative log answer, whatever that is, away from the number 14. So if I do negative log of 1.0, it's 0. So I do 14 minus 0. The pH of this solution would be 14 pH units. Okay. This next one has got a typo in it. I'll have to fix it for next time around. The other ones are correct, though. You know, you do negative log of 0.01, and you take 14 minus the answer, and you get a pH of 12 pH. Okay, so that's the mathematical foundation of the pH scale. But what I really need you to understand is that each step represents a 10 times change, 10-fold, 10x. So each step you multiply by 10 for your concentrations as you go. So let's look at some of this. There's definitely going to be some of these around. So when we go from a pH of 4 to a pH 5, both the OH concentration changes and the H plus concentration changes. So we go from 4 to 5, becoming more basic, because basic's over here, acidic's over here. Becoming more basic, so the OH concentration increases by a factor of how many times is each step? By 10 times, by 10x. That's all there is to it. Now, the other side of the coin is whenever OH increases, the H plus has got to decrease because they're opposites. They only neutralize out at 7, so become less acidic in this scenario. H plus decreases, and if the one increases by 10, the other one's got to decrease by 10. Okay. The next little bit is when we have to skip more than 1 pH unit. It's easy to remember 10 times, but If we're going to go from pH 13 to pH 10, we have actually skipped 1, 2, 3 gaps there. So in this scenario, we're becoming more acidic. H plus increases. Now here's the trick. Many people will screw up and say by 30 because they counted 3 steps. And they're like, well, 3 times 10 is 30, right? No, each step is 10 times. So it's 10 times 10 times 10, or 10 cubed. And the cubed part comes from the number of steps. If you went 4 steps, that'd be a fourth. 5 steps, you'd be the fifth. You multiply 10 each time you go. Now let's look at the opposite. If the H plus concentration increased, the basic has to decrease. So becoming less basic, OH negative decreases by 10 times 10 times 10. That equals 1,000. The same amount that the acid increased by, the base decreases by. That's all there is to it. Now, some simple solutions of household things do have pHs. Okay. Battery acid's the nastiest stuff out there. Lemon juice is pretty gnarly too if you get in your eye, but lemon juice generally won't scar you. Battery acid would. So the kind of the dividing line between gonna hurt you and you can eat it is pH 1 or 2. So I wouldn't suggest eating battery acid. I think it would hurt you a lot. Other things, notice again, bases, OHs, OH, 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 all over the place. Okay. Except for that pesky ammonia, which behaves differently. Now, strong acids and bases ionize 100% in water, which means they completely dissociate. NaOH becomes Na positive and OH negative. HCl becomes H positive and Cl negative. Weak acids and bases don't always do that. Weak acids and bases, some of them stay as the stuff they came in, and some of them ionize. So actually I have to draw a third line here. So some of this stays as H2, C2, H3O2 acetic acid, and others actually break apart into and then C2H3O2 negative. Got a couple animations to show you for this one. So all courtesy for these animations goes to the Guelph University's acids and bases little tutorial. So when I add a strong acid to water, H out front for acid, it completely dissociates into H plus and X minus, which the H plus then hops on through a coordinate covalent bond to the water molecule, and you get complete dissociation. All the acid becomes ions. Okay, rewind that one. Now let's look at the situation where we have a weak acid. If I add a weak acid to water, some of these things are going to dissolve just like regular, and others are going to deionize or ionize, dissociate like strong acids would. So the reason that it's a weak acid is because not all of them dissociate. Okay, so that's the difference between a strong acid and a weak acid. So go back to the presentation here, and we got to go down and talk about ammonia. Ammonia is a special situation. Ammonia likes to hydrogen bond with water, and it's so powerful at it, it can steal a proton, let's say NH4 plus, NH4, and OH negative. So the deionization of ammonia, it can actually steal a proton away from the water, making a scenario like this. I'm going to go back here. So I'm going to add some NH3 to water. Ammonia is a gas, typically, which means that you have to dissolve it in water, and it's only slightly soluble. Weak bases will come in and steal away a proton from the water. So here it comes. There's an ammonia molecule in the middle, bumps into a water molecule, and steals a proton away from it, making an OH negative and an NH4 plus. Now, the thing you got to notice in this simulation here is that not all of the NH3s are doing this. Many are doing nothing. They're just chilling out in the water as NH3. Some of them are able to steal that proton away from water, and as a result, make the solution basic. So here we go. They're highlighted, those ones there. But most of the ammonia is kind of doing nothing, which is why it's a weak base. If it was a strong base, all of the ammonia would become ammonium, NH4+, and all of the water would get its protons stripped away from it. So that's the basic reason behind why ammonia is a weak base and doesn't have the OH in it, because it kind of makes its own OH when it bumps into a water molecule. And this is a coordinate covalent bond. Covalent bond. It steals the H, steals the H plus away from the water. Okay, so at this point, you should at least understand how each step on the pH scale relates to a 10 times change in concentration. Don't just do 10 times however many steps you got, because that'd be like 10 times 2 times 3, that'd be wrong. You gotta do 10 times 10 times 10. For every step, multiply your answer by 10 again. And understand those basic difference between strong and weak acids. How strong ones dissociate completely and weak ones don't. And so in our practice pack, we got about 3 pages of practice on this material, and we have a Castle Learning quiz for you. At this point, you should probably be able to do that, the first one, the prep, about the theories. So thanks for watching. Have a good day.